I recently did a video on why laser light was special. To boil it down, laser light's special because the photons are all moving in the same direction, the same phase, the same frequency, and this is referred to as coherence, while normal light from the sun or a light bulb is disordered and incoherent. Laser light is different than regular light for the same reason that a baseball flying through the air is different from a baseball that is just slightly warmer than its surroundings. In both cases, the molecules of the baseball are moving slightly faster, but in the former case, all the molecules have extra velocity in the same direction. And in the latter case, the velocities are all in random directions. It's the same coherence versus incoherence issue. Check that video out if you want to expand on that idea. It got me thinking about another interesting thing about lasers, which is their diversity. Almost anything that works as a light source, you can slap some mods on it and make it into a laser. For example, LEDs emit incoherent light, and with some modifications, you can make that into a semiconductor laser. Neon signs and fluorescent lights use an electrical discharge to make light, and with some modifications, you can use an electrical discharge to make, for example, a helium neon laser or a carbon dioxide laser. You can emit light from fluorescence or phosphorescence, and then these phenomena can be used to make a ruby laser or a dye laser. It's really amazing how many different flavors of laser there are. For something that seems so complex and mysterious, it raises the question, why are there so many ways of making it work? I mean, what are the core principles behind a laser? I just wanted to explore that in this video. So before starting, I've got to take a moment to just review the physics behind the laser, because otherwise the later sections just won't really make sense, and also because I never really liked how this is usually explained in textbooks. So I just want to introduce a few quick background facts. So first off, light is an electromagnetic wave. Light is also a particle at the same time. First, it was believed by Newton to be a particle, and then Huygens developed the wave theory of light, which was proven by diffraction and interference experiments. And then Maxwell showed that light was an electromagnetic wave consisting of a transverse electric and magnetic fields. And in these illustrations, I'm just going to show a one-dimensional wave, and I'm just going to talk about the electric field, but you should always be aware that there's also a magnetic field at 90 degrees that I'm just not showing and I'm not really talking about. Now, a few things about electric fields. The first is that they are vectors and they add like vectors. If you have electric fields from two sources, then the net electric field is just the sum of the two vectors. The second thing to know is that there is energy associated with electric fields and that it's proportional to the electric field squared. If you have a certain electric field, if you then go and double the magnitude of all the electric field vectors, then the energy will quadruple. And as I said before, also light is particles. It seems like everything was settled until Einstein did some work interpreting the photoelectric effect and found that the data could only be explained if light came in packets with a certain amount of energy and momentum. And the energy of a photon is proportional to its frequency, and also the momentum is proportional to its frequency. Now, an electromagnetic wave flying across a room could look something like this wave packet. You could figure out the energy of that wave by squaring the value of the fields and then integrating. Now, you could also figure out the frequency, and you could calculate the energy of the associated photon. And these may not be the same. For example, if you have two wave packets, they may have the same energy determined by the integration of the fields, but one has twice the frequency of the other. Now, that just means that one wave packet will be associated with twice as many photons that each have half of the energy. Anyway, atoms can absorb photons, and the absorbed energy will increase the energy of an electron. Now here I'm showing electrons like they're orbiting planet nucleus, but I'm sure everybody appreciates that that's not how it works. The electron orbitals themselves are, you guessed it, waves. Because just like light is both a particle and a wave, so is matter. So is everything. But it's too hard to draw the wave that represents the orbital, so I'm just going to go with the old planetary model you see in kids' books. Anyway, there are a lot of rules around the electron jumping between orbitals. You have to conserve energy, angular momentum, and likewise, an electron can fall down to a lower energy level and emit a photon, provided that certain rules are followed. Last piece of background info I want to introduce. What is the frequency of this wave? Well, you could measure the distance between the peaks and give me an answer. Now, how about this wave? I mean, I guess it's the same. How about this one? How about this one? Does this still have a frequency? At what point does it stop having a defined frequency? Anyway, the truth is that for a wave to have a definite frequency, it has to go on infinitely in both directions. And as you shorten the wave into a smaller packet, the frequency is no longer a single number. It's actually a distribution of different frequencies that are centered on whatever the original frequencies were. It's a distribution, it's like a bell curve, and it gets wider as the wave packet gets narrower. If you want to put that photon through a prism, it's not going to be a single infinitely thin line. It's going to fatten out a bit. And so that's Fourier analysis, and it's just a little bit too much for this video, but I wanted you to be aware that spectrally pure electromagnetic waves, they go on infinitely. So this is all kind of boring, but I needed to set the stage for what laser light is. So we know that it's spectrally pure, just one frequency, just one direction. We have normal photons going through space. They're going to look something like this. Whereas laser light, we know that because of the stuff we mentioned previously, it has a narrow frequency distribution, all the same direction, so it must look something like this. So if we have, for example, a neon sign that puts out light like this, then how can we get that to be like this, like the output of a helium neon laser? This is where we start to get into Einstein's contribution to the development of the laser. I'm going to explain this in a little different way than it's normally explained because I think the normal explanation tends to gloss over the important part. Remember when we talked about how an atom could absorb a photon or it could emit a photon? There's some probability of each. So that seems pretty simple, right? Now, what Einstein said was, hey, there's actually an edge case here that we have to consider. So what if the atom emits a photon at the exact same time that another photon is going by? Now why would that matter, you say? Well, okay, so suppose that the photon going by was like this and the emitted photon was like this. We said earlier that electric fields are additive, so the net electric field would be this. Basically, the photons just annihilated one another. But that breaks conservation of energy. Before, you had a photon with some energy and you had an excited atom with some energy, and now you have no photon and you have an unexcited atom. Energy just disappeared. So obviously that is not allowed. Now, alternatively, what if you have something like this, where the emissions line up perfectly? Well, that would double the amplitude everywhere, but that's not allowed either, because remember that the energy goes as the electric field squared. So if you double the amplitude, but you have 4 times as much energy. So before, you had one photon and one excited electron, and now you have 4 photons worth of energy. So you created energy out of nothing, so that can't work either. So there has to be some synchronization of the emitted photon so that it interferes in such a way that you get the same amount of energy. Now that may look something like this. And notice what happens. The wave gets longer. It's more spectrally narrow, and they're moving in the same direction. So this is a special case. There are actually 2 different ways that an atom can emit a photon. It can emit one spontaneously, which is called spontaneous emission, or when another photon is nearby, and that is termed stimulated emission. Now, Einstein worked out the thermodynamics of this, the relative populations, the relative probabilities of each type of emission happening. And that's usually how people present Einstein's contribution to the development of the laser. But I think the important part is actually this initial insight that there are 2 distinct types of emission, and there have to be. That's the important part. Now, I bet you can see where this is going. Imagine that happens multiple times in a row. You're going to lengthen out the wave packet each time, and it's going to start to look less like the single photon wave packet and more like the long laser wave. Fundamentally, that's how we make a laser beam. So on a practical level, what do we need to do to make a laser? We need to figure out a way to get a bunch of these atoms lined up so that the wave packet can lengthen out. So the first thing we need is a really, really long tube to get a bunch of atoms lined up. There are different ways to do this. One of the ways that you can get a really long tube is to just have a really long tube. That's called a fiber laser. It uses a long coil of fiber optic cabling, and the light travels down the cable. Fiber optics are able to bend light smoothly to travel along the pathway, so the fiber can be wrapped up in a coil. Even though it may be thousands of meters long, it can stay wrapped up in a relatively compact coil. But more commonly, you use a tube with mirrors on each side. One of the mirrors is a partial mirror, so the light bounces back and forth many times before exiting. So for all intents and purposes, it's a super, super long tube. The other thing you need is a way to get all these atoms in an excited state waiting for a photon. And that is harder than it sounds, because if you just get the electron to jump up in energy levels, either by whacking it with an electron or a photon of even higher frequency, well, it usually just falls right back down, rather than patiently waiting around for a different photon to travel by to do stimulated emission. You need to set up what is called a population inversion, where there are more atoms in the excited state than in the ground state, which is a very unusual situation because normally excited atoms immediately fall right back down. So the way you do this is by figuring out what is called a metastable state. This is a state where an electron gets stuck and it takes an extra long time to relax. It's not stable. It does relax eventually, but it takes a long time, so that we say that it's metastable. Now, you can't excite directly to a metastable state because it's a transition that the electron doesn't like to make. Just like it can't easily fall down, it can't easily jump up to that state. But what you can do is excite it to an even higher state. Then in some cases it can lose a little bit of energy, for example, bumping into another atom and losing thermal energy or other perturbations, and then it's stuck at the metastable state and it can wait around to do stimulated emissions. Now, metastable states are going to depend on the material itself that you're working with, and you essentially discover metastable states for each different type of matter, and once you have discovered it, you know that you have something that you could potentially use as a laser. So those are the two things that you need. You need a resonant cavity done by mirrors or fiber optics or whatever, and then you need a way to generate a metastable state. And there are lots of ways to do this and many techniques that you can use to create light that can be tweaked just a little bit to make a laser. Now, how to make a specific type of laser, there are always tons of little details that make it difficult. But in broad strokes, it's actually not too complicated.